Hi everybody, today we're talking about the MAT17B discussion sheet number 3. Okay, the first problem asks, in chemistry, one often measures chemical reaction rate, which gives the change in concentration per unit time. Suppose you know how the concentration of a chemical varies with time, that is, you know dc dt, or the derivative of c with respect to t. With respect to the concentration of the chemical, interpret the following integral. The integral is from T1 to T2 of dc dt, integrating with respect to t. Okay, so this question depends upon the fundamental theorem of calculus and understanding that the integral operator and the derivative operator are inverse. So in other words, when we integrate a derivative, we're really just going to get back the original function, and when we take the derivative of an integral, we get back the original function, or the function inside. Okay, so here we have the derivative, or excuse me, the integral of the change of concentration with respect to time. So if we integrated that over the entire domain of the time of the change in chemical concentration, then we would get the concentration at any given time. So in other words, if we started, and time here starts with 0, so if we went from 0 to some big T of dc dt with respect to t, we would get the concentration at time t. Okay, so if we imagine a picture of this, if we have some dc dt curve, okay, and we integrate from 0 to time t, that gives us c at time t. Okay. Now, instead, though, we're integrating from some time t1 to t2. So let's remember that using properties of integration, we can say that this is the integral from 0 to t2 of dc dt, the integral with respect to t, minus the integral from 0 to t1 dc dt with respect to t. Okay? And when we integrate these using the fundamental theorem of calculus, we get that this is C of, the concentration at time 2 minus this is the concentration at time 1. Okay, so this is the concentration at a specific time, and this is the concentration at another specific time. So if we subtract them, we're getting the change in concentration from time 1 to time 2. So if we imagine what we've done, oops, that's not what I wanted. These are axes. So we have some function that represents dc dt. Okay, what we've done is we've integrated, if we integrated from 0 to t2, that would be this entire area, but we've taken away the integral up to t1. And so this area, the integral from T1 to T2, is the change in concentration from T1 to T2. A lot of people said concentration from T1 to T2. That doesn't make sense, right? So concentration is a measurement of how much we can expect of the chemical per unit of solution. Now, if I just said the concentration from T1 to T2, that doesn't mean anything. That's nonsense. So we need that change in concentration. Okay. Okay, problem 2 says, suppose that you measure the flow rate of blood in an artery. You find that your measurements are well fit by the equation dV dt is equal to 10 minus 2 cosine of 120 pi t in units of milliliters per second. Okay, milliliters per second. So what volume of blood flows through the artery in 10 seconds? Okay, so again, we're going to integrate this change in volume to get our change in flow rate, the change in flow of blood. So flow rate of blood is dV dt, to get the total volume. Okay, so if we integrate, and I'm just going to do the indefinite integral for now. of this function. So the integral of dv dt with respect to t is the integral of 10 minus 2 cosine 120 pi t dt. Okay, now 10, that's easy to integrate, right? We just end up with 10t. Okay, and now for this other one, we know that we're going to have sine of 120 pi t, right? Because we're going to want the antiderivative. So we want something that when we differentiate it, we get cosine. That, of course, is sine. And we want there to be 120 pi t inside, so we leave that there. But let's remember that when we differentiate, we take the derivative of the outside, that's cosine, so we get cosine of 120 pi t. But then we would also, because of the chain rule, take the derivative of this inner piece, which is 120 pi t, so the derivative is 120 pi. So if I take the derivative of this function, sine of 120 pi t is 120 pi cosine 120 pi t. So here we just have a 2, so we need to divide by something, some constant, so that instead of 120 pi, we just have a 2 sitting there. Okay, and that value is 1 over 60 pi. Okay, so if I take the derivative of 1 over 60 pi sine of 120 pi t, let's just check our answer. We get 120 pi over 60 pi, cosine of 120 pi t. Okay, of course that simplifies to 2 cosine 120 pi t. Okay, so here another way of doing this that you know now is to make the u substitution u equals 120 pi t. So then this 1 over 60 pi will come out because you'll have a du factor sitting there. Okay, now the question isn't just what volume of blood flows through the artery, period. It gives us some time interval that we should integrate over. Okay, so what we really want is the integral from 0 to 10 in 10 seconds of dv dt with respect to t. And we could do this for a general time t also, which would be a good thing to practice. But let's just do it from 0 to 10 for now. So this is 10t minus 1 over 60 pi sine 120 pi t evaluated, right, from 0 to 10. Okay, so to complete this problem, I would insert 10 and calculate this value and then subtract this value at 0. What volume of blood flows through the artery in 1 minute? Include units. Oh, and I'm sorry, the units, I almost forgot. So we've integrated milliliters per second with respect to time measured in seconds. So of course we'll just get milliliters. Okay, now what volume of blood flows through the artery in 1 minute? Of course we'll just do the exact same thing, except for instead of doing for 10 seconds, we'll do for 1 minute or 60 seconds. So this is the integral from 0 to 60 of dv dt with respect to t. And actually, just for fun, let's take this from for any general 60-second period. So let's go from t to t plus 60. Okay, so this is, we get the same general antiderivative or indefinite integral, 10t minus 1 over 60 pi sine 120 pi t. And then we're going to evaluate from t to t plus 60. Okay, so to finish, we would plug those values in and subtract. And then, of course, this is in milliliters also. Okay. Okay, the third problem says, suppose that you measure the density of sea urchins on a particular shoreline. You find that your density measurements are well fit by the equation W of x equals 1,000 over x in units of number of sea urchins per mile. Okay, so what this is telling us is that this, whatever our measurements were they're well represented by a function that's defined for all x, okay, so for all distance along the shoreline. Okay, so this is going to be changing, so as you move along the shoreline, the density that we expect is always constantly different, right? For x equals 0.1, it's different for x equals 0.2, and all values in between. So how many sea urchins are there between mile 1 and mile 2? Okay, so density is urchins per mile. Okay, so urchins per mile. So if we want to get the number of urchins, we want to integrate with respect to distance in miles. Okay, so let's integrate this value, w of x, with respect to distance or length along the shoreline. And we're going to integrate from mile 1 to mile 2. Okay, so this must be distance in miles. This is per miles, so everything checks out. So we get the integral from 1 to 2 of 1,000 over x dx. Okay, so let's remember we can pull out this 1,000 and just integrate 1 over x, which is the natural log of x when we integrate. And then we're going to plug in 1 and 2. Now, this is 1,000 natural log 2 minus 1,000 times the natural log of 1. So the natural log of 1 is, we can rephrase that as what do we have to raise e to get 1? Well, of course, that's 0. So natural log of 1 is just 0. 1,000 times 0 is 0. So this is a minus 0, so we leave that off. So 1,000 natural log 2 urchins. Okay, we integrated with respect to miles, so we just get urchins. What is the average density of sea urchins between mile 1 and mile 2? Okay, so now what we're going to do is we're going to integrate to get the total number of urchins between mile 1 and mile 2, and then we're going to divide by the distance. Okay, we already have the number of urchins, so this is 1,000 natural log 2 urchins. Okay, and then we need to divide by the distance over 1 mile. So this is 1,000 natural log 2 over 1, which is just 1,000 natural log 2 urchins per mile. On average, that's the density of sea urchins between mile 1 and mile 2. Now mile 1 and mile 3, we're going to have, if we do this same integral from 1 to 3, we get 1,000 natural log 3 urchins over the distance, which between mile 1 and mile 3 is 2 miles. Okay, so the average density of sea urchins between mile 1 and mile 3 is 1,000 natural log 3 over 2 urchins per mile. Okay, the fourth problem asks, suppose you are measuring the growth of a bacterial colony. You monitor its growth over 10 days, measuring its growth rate each day. To do these measurements, you count the number of bacteria at 10 a.m., then divide that number, and then the number at 11 a.m. The growth rate is the difference in the population divided by the time between measurements. So for example, if you measured 100 bacteria at 11 a.m., and there were 50 at 10 a.m., the growth rate would be the difference, right, 100 minus 50 over 1 hour, but we want to get it into bacteria per day, so we multiply by 24 hours per 1 day. So we get 1,200 bacteria per day. Okay. So we have these data that we've measured, and we're going to plot them along with our equation. The growth rate is 4.0553 times e to the 1.8t. Okay, so we've given you all of the RStudio commands, so I'm just going to explain them as you follow along. So first, let's define t. So t is going to be a list that just holds the time. So first, we'll have it start at 0, so from equals 0. 2 equals 10. Okay, so we go from 0 to 10, and we're counting by ones. And this counts the days. And notice we use a sequential list. So SEQ tells the computer to create this list by counting sequentially. So So when we press enter, we see we have a list of 11 numbers that go 0, 1, 2, just like we want. Okay, now let's enter the G data. Okay, so here I've just entered all of the numbers from our data table. And we should always check and make sure here we have an 11 list. These numbers need to match up or we won't be able to plot them. Okay, now we define the equation 4.0553 times the, e to the 1.8t. So for RStudio, e is known as exponent, so exp of 1.8 times t. And so this will take all of the values in t, multiply them one by 1.8, raise e to that number, and then multiply by 4.0553, and store it in a list that's called G underscore equation. Okay, so when we press enter, we see G equation is a list of 11 numbers, and those are what we would like to see. Okay, and now let's plot. So we always need to plot first. Okay, so plot T G data. So this creates our plot that we see over here. And now we can add a line of the equation. So lines T G equation adds to the originally created plot. Okay, and now we've completed the first part of part A, and it asks us, based on this plot, do you think this equation fits the data well? Choose one of the following: yes, no, hard to tell, and explain. So this is really whatever you thought you saw. Personally, I think it's pretty hard to tell. If we look at the y-axis on the plot, notice that it goes from 1, right? 10 to the 0 is 1, all the way up to 3 times 10 to the 8th. That's a huge number. So the scale here is huge. So these little errors that maybe we can't even see, for example, here we can see that there's some sort of an error. They could be huge, right? They could be thousands of units. So my guess there would be that it's pretty hard to tell. Okay, and so the idea here is that while when we have scales that are huge on either axis, but especially on the y-axis, by taking the logarithm of those values, it makes the error a lot easier to see. So if we now take the logarithm of the data, okay, so G log data is the logarithm of the entries in G data. Okay, notice we get this length 11 list of the logarithms of G data. And we're going to do the same with the equation G. Okay. Okay, now let's plot the log data. Okay, notice it's already, the scale is much better. We go from 1 to 20 rather than 1 to 20 or 1 to 10 to the 8th. Okay, now let's add a line for the log equation. And now we can see that it does in fact fit well. Okay, now we're on part C. So part C asks, if P of t is the population in number of bacteria at time t, what does the growth rate G of t represent? I.e., write G of t in terms of P of t. Okay, so growth rate, that just means the change in population given the change in time, right? Change in population for instantaneous changes in time. So that's exactly just the derivative of population, right? The instantaneous rate of change of population. If the initial population is 46 bacteria, or the population at time 0 is 46, find the population 4 days later, assuming that G of t is 4.0553 e to the 1.8t. Okay, so here we want to find P of t. So and specifically we want P of 4, right? But let's work through it completely. So this is the integral of P prime of t with respect to time, which is the integral of g of t with respect to time. Okay, and so the integral g of t is 4.0553 e to the 1.8t dt. Okay, so when we integrate this, we get 4.0553 over 1.8 e to the 1.8t plus some constant c. Okay, so now we have to remember that we have this initial value. So at time 0, so if we plug in 0 for t, we should get 46. So in other words, we should get that 46 equals p of 0, which is 4.0553 over 1.8 times e to the 1.8 times 0 plus c. Okay, so e to the 1.8 times 0, this is 0, so this is e to the 0, which is 1. So we get that 46 equals 4.0553 over 1.8 plus c, which then tells us, let's go down here, c is 46 minus 4.4053. Sorry, this should be 4.0553 over 1.8. Okay, so now if we want to find P of 4, okay, so P of 4 is 4.0553 over 1.8 e to the 1.8 times t, which here is 4, plus c, which we know is 46 minus 4.0553 over 1.8. Okay, so this is the population 4 days later. So we have to use this fact to find our constant. Then we can we have completely determined the function p of t because we know c here, and we can just plug in time equals 4 for t. Okay, if the initial population is 46 bacteria, find the population at some time t, assuming that g of t. Okay, so we've already done this. We know the function for p of t, and we know what c is. So we've completely determined p of t, given this starting initial population. P of t is 4.0553 over 1.8 e to the 1.8t plus c, which is 46 minus 4.0553 over 1.8. Okay, so that's our population at any time t. So find the population at some time t, that's just telling you find a description of the population as a function of t. Okay, now it says, check your answer to part E by calculating the change in population per unit time and recovering the equation for growth rate, g of t. So in other words, we need to check that when we take the derivative of our population function, we still get back g of t, okay? So p prime of t, let's take the derivative of this function. So when I take the derivative here, I get e to the 1.8t, and I pull down a 1.8, which cancels there. So this is 4.0553 e to the 1.8t. And then, of course, this derivative of a constant goes away. That's just 0. So we recover g of t, just like we should. So we've sort of checked that when we integrate up and then differentiate down, we get back the same function. Okay, now for the Fermi problem, what percent of the ground in Davis is lawn? So here we're just expecting that you will give us some assumptions, some reasonable assumptions to in order to calculate this. So to begin with, I'm going to say that, and I don't know if this is reasonable at all, but I'm going to guess that 20% of Davis is cement and let's say like streets and commercial. So lots where there won't be any lawn, like when you go downtown, there's no lawn in front of most stores. Okay, so now I'm working with 80% of Davis is is houses, right? Is lots, and I'm going to say that every lot is half. Every lot is 50% lawn. Okay, so of my 80% of Davis, that's lots. Every one of those lots is 50% lawn. So the percent of ground of lawn is 80% times 50%, right, which is 40%. And I could do a similar thing for California, but don't need to.